Good morning, everyone. I'm Gay Yee Hill. It's 3:10 a.m. Pacific Time at NASA's Jet Propulsion Laboratory in Pasadena, California, 6:10 a.m. on the East Coast, and 10 minutes past noon Central European Standard Time. It's a bittersweet day for space exploration. The European Space Agency is ending the Rosetta mission. Rosetta was launched in 2004. It took 10 years to get to Comet 67P Churyumov-Gerasimenko. It's the first mission in history to rendezvous with a comet, escorted as it orbited the Sun. Its lander, Philae, obtained the first images taken from the surface of a comet. Now, NASA is a partner in this mission, and the Deep Space Network at JPL will be supporting ESA's ground station network for spacecraft tracking and navigation. Yesterday, ESA commanded Rosetta to change course, a maneuver that puts the probe on a direct collision course with a comet. Rosetta's last act, currently underway, is a death dive.
If we don't take risks, we don't break the barriers.
We've never done anything like this before.
Rosetta discovered so many interesting things about comets.
Rosetta is a very ambitious mission.
This last chapter of exploration is something really daring.
We're going to have what we're calling a controlled crash.
The orbit is going to be modified in such a way that the spacecraft gets closer and closer.
Before finishing with a soft landing on the small lobe, which we would call the head of the duck, as this is kind of duck-shaped.
We're going to go right down, right into the surface, taking photos, taking measurements.
Comets, these are the building blocks of the planets. So we can look at kind of where we all came from.
The mission is only the ending, in my opinion. In my sense, it's almost the beginning.
I think we still have a lot to look forward to. There are discoveries yet to be made.
The most exciting discoveries are ahead of us. The best is yet to come from Rosetta.
ESA says Rosetta's estimated time of impact is expected to be around 4:18 Pacific Time, 7:18 Eastern. We'll be cutting over to ESA's coverage in a little while. Until then, we'll chat with folks at the European Space Operations Center in Darmstadt, Germany, to get a sense of what things are like over there. And in the meantime, I'd like to introduce Steve Chesley, a senior research scientist with NASA's and JPL's Center for the Near-Earth Object Studies. And Steve's our resident expert on asteroids and comets. Tell me why this particular mission is such a game changer in terms of our knowledge of comets.
Yeah, Rosetta has been really spectacular, and one of the reasons, I think, is because it's been so long and so close to the comet. Before Rosetta, we had a number of fast flybys. You have a few moments and you take a few pictures of a comet that you're flying by, maybe at hundreds of kilometers distance. And being able to stay with the comet for 2 years as it goes through perihelion, you see how lively the comet is. It's a sort of a dynamic, active place. We can see geology happening in real time. We've never been able to see with the fast flybys where you get just one picture or a few pictures at one moment.
So this gave us in-depth study, so to speak.
Yes, and the Rosetta spacecraft has a suite of 11 instruments. So there's so many scientific investigations and so much science data that's coming down from the spacecraft that's going to keep folks busy for many years to come.
All right. Well, Steve, you'll be staying with us throughout this program. And meantime, we're going to check over to the European Space Operations Center in Darmstadt. That is where Rosetta's project scientist, Matt Taylor, is kind enough to take some time to talk to us. Matt, thanks so much for joining us.
My pleasure.
First of all, congratulations. It's been such a successful mission. Can you explain what's going to be taking place just a short time from now?
Okay, last night, our time in Europe, we carried out a collision maneuver and that put us on course to impact with the comet. And in a few hours' time, we will do that. We'll impact, and that's the end of this mission, the end of this odyssey that we've had for over a decade now.
Why did ESA decide to end this mission this way?
Well, as we've heard, the Rosetta mission was designed to escort a comet around its closest approach to the sun, and we're going away from the sun. We're moving away from the sun now. We're getting into a condition where the spacecraft hasn't got enough power to keep everything going. We've had to switch certain parts of the payload off, including some parts of the instruments, but not all of them. And we're also getting further away from the Earth. That means we're getting lower data rates. So we're getting something like about less than 10% of the data rate we were getting during the summer last year. So we're getting to a point where there's not much left in terms of what the spacecraft can do. We'd have to either switch it off, just leave it there, and put it into hibernation. This was the option where we'd maximize the science. We'd get as much as possible out of the system before we have no time left and we have to switch things off. So it's really, this weekend, we start to go behind the sun as well with respect to the Earth. So we go into conjunction, we'd have no data rate. So this is the last day that we could do any science. And in some ways, I think it's a fitting end to this mission. It's been a roller coaster, and this crash and burn that we're going to do is really fitting for the way this mission has been run. And it is a fantastic science mission.
Well, Matt, tell me why you picked this particular landing spot, though.
Okay, well, the head of the duck, let's describe the comet as a duck. It's the easiest or the least difficult place to land on the comet. We showed that with the Philae landing when we were selecting sites there. From a gravitational perspective and illumination, it's the best place to land. Now, specifically the matte region on the kind of left-hand side of the head of the duck, that area has these pit regions. These are like sinkholes on Earth. They're a few hundred meters across, deep cylindrical pits, and the sidewalls have these fantastic goosebump-like structures, like loads of tennis balls racked together, around meter to 3 meters in scale. And they are giving us a view of how the comet was put together. In addition, the way we're doing this final dive from last night, from about 20 kilometers down to the surface, we're not doing anything with the spacecraft in terms of maneuvering it. So we have a very clean profile as we approach the surface of the comet. In particular, in the next few hours, we're going to get below 2 kilometers from the surface, and we've never reached into that area of the coma, the outer atmosphere of the comet. And that's the important bit. There's unique science that we'll get just from seeing, and what we're interested in is where the ice and dust that is the comet, how that goes into the coma. How does it become the coma? This acceleration region, we call it, which is in this short 2 kilometers from the surface. We've never been in there. We've looked at it from a remote sensing point of view, but we've never tasted it, as it were. And that's what we'll get just before the end.
And so you're getting information right down to the very end. That was the objective.
And the way we're doing this is to just basically, we're live streaming straight. As soon as the instrument takes the data, it's firing it back to Earth. And thanks to DSN, we're getting a good downlink rate as well. So, thanks to people like Amanda who've negotiated for us to get the DSN time. And that's really helping us here, because otherwise we'd get a third of the data we're capable of getting. So it's really good that we've got that. And it's all coming down live. And it will stop. And that means the end. So those of you familiar with Rosetta in 2014, in January, we came out of hibernation. We were watching this trace, this carrier signal that wasn't there, and then all of a sudden this peak came up. Now in the MCR, the main control room, we have a similar plot with the carrier signal in the middle. When that disappears, Sylvain Laudiot, the SOM, the spacecraft operations manager, will make the comment that this is it. That's the end of Rosetta. So it's kind of the opposite of what we had in January 14.
All right. Well, we'll be standing by and we'll be watching right along with you. Thanks again for joining us.
Thank you. Thank you.
And Steve, well, let's take a moment and kind of cover the area that Matt just described. Where about on the comet is he talking about?
Yeah, so here's a model of the comet. You mentioned there's 2 lobes. It looks like a rubber ducky. You've got your body and the head, and right here on the left side of the smaller lobe is where we'll be landing. Incidentally, the Rosetta lander Philae is over here on the right side of the head. And this is just adjacent to one of the pits that we saw a few moments ago on the screen. This should be landing right next to it, and the point is to get pictures looking down inside the pit. One thing to mention is that appearances can be very deceiving in space exploration. This looks like it's sort of potentially a big rock that you could.
You're right. When we see these images, they look like rocky surfaces that hard, Earth-like, but they're nothing like Earth.
And one thing I should mention: the images show a sort of a large gray body, but actually it's black. It's like the color of charcoal. It's more like the color of this model that I'm holding, is the actual what you would see if you were there, and it's very light. This is about half the density of water. If you could lower it gently into the ocean, it would float, and you can picture, say, it's about the same density as a piece of wood you might get at the lumber store.
So like a 2x4.
Yeah, exactly, and it's about 70% empty inside. And it's the strength of this body, these two lobes, for instance, the way they're held together, and even the lobes themselves, the strength is very weak. You should think more about dry snow, the strength of dry snow, where it would just crumble in your hands without even putting much pressure on it.
So this is a very light, airy mass.
Yeah, well, of course, it's what we say is void space. Most of this object is vacuum.
And so landing something on this, we're crash landing it, we would envision something just, smashing to smithereens. That may not happen in a case like this.
So the Rosetta spacecraft is going to come into contact at a little bit slower than you might walk across a room. Okay. It's very slow speed impact. Of course, it has solar panels that are something like 100 feet end to end, and so that's what's going to probably first come into contact, and as soon as that happens, it's going to come off its orientation. The antenna is not going to be pointed at Earth anymore, and we won't see any more of Rosetta.
And we should add, this was not a part of the original plan, right? Rosetta was never meant to be a lander. It was always supposed to be an orbiter.
It's an orbiter. It had a lander, and it landed a few months after arriving at the Comet, and that was a spectacular success in terms of the science return from the Philae lander.
So we won't get a scenario where it will drop and fire thrusters or anything like that, because it was never meant to be in a situation like that. It
fired its thrusters yesterday around midday, in California at least, and since then, it's just been essentially coasting, uncontrolled, to the surface of the comet. And it's sort of a testament to how well the navigators are able to control the spacecraft, that they can let it coast for close to a day and have it come down within a few hundred meters of its target location.
All right. Well, we'll catch up with you a little bit later on that. Meantime, this is a day that NASA is very excited about, too. Joining us now is NASA's Director of Planetary Science, Jim Green, who is also at ESA in Germany for this big event. Jim, can you tell us a little bit about NASA's role in the Rosetta mission? We mentioned earlier that we're a partner in this. Can you be a little bit more specific and let us know how was NASA involved?
Well, we have 3 full instruments on Rosetta, the main spacecraft, and then a part of another instrument. And that's very important for our scientists to work together as a team. Those measurements are critical in terms of understanding a lot about the cometary surface structure, its heat, also about, as it sublimates in the sun, how the material then moves around into a coma and then interacts with the solar wind. All the physics of that, these instruments are very much involved in. And then the part of one we have is the part of the Rosina instrument, which then really sniffs out and smells the things that are in the comet. Now, we didn't have any instruments on Philae, but all on Rosetta.
But I understand quite a few U.S. scientists were parts of other teams as well.
Oh, yeah. It's in this mission in particular, ESA has really reached out and made it so international. In fact, I can't remember a mission that's more international than Rosetta. So not only are there NASA scientists, but many other scientists from many, many countries. And it's a natural connection our scientists have. They work as a team no matter what the country boundaries are.
How important is international cooperation in space exploration, especially in this day and age?
Well, it's very important for many reasons, and the first one we've already addressed, which is really about connecting our scientists together, and we do that with the data and the missions that we work together on. We want the best ideas in understanding what these observations are telling us, and so scientific thinking is not unique to any one country. Now, in addition to that, there's also the opportunity to be able to leverage resources. Sometimes the sum is greater than the individual contribution. And each of these countries that contribute to Rosetta, gets really a big bang for their buck, so to speak. And that's certainly true with NASA. ESA has been a tremendous partner. It's been our best partner year after year after year. We do so many wonderful things with ESA that the environment is just great for international cooperation right now.
So, Jim, what's next? More Comet missions?
Well, planetary science has a methodology. It's flyby, orbit, land, rove, return samples. And for comets, we have had a number of flybys. And we've kind of pushed the envelope and actually returned some samples from a coma, the extended atmosphere of a comet, with one of our missions. But it's really now going to be all about getting down to the surface and getting a sample and bringing it back. Getting under the dust layer, seeing what some of that fundamental material is like, the ices that have conglomerated along with the dust that it is trapped inside, and what that matrix looks like and how it holds all together. And that's one of the major concepts that we've been thinking about for quite a while. And this next year, there may be some proposals that will come to NASA that will indeed go after that.
All right. Well, we will have a wealth of information from this mission, and we will be studying it for decades to come, I'm sure. Thanks, Jim.
Well, just
go ahead.
My pleasure. Yeah, and so just let me build on that a sec, because when you think about what's happening today, they are landing the large spacecraft down on the surface. Now, we may not learn anything significantly scientifically, because ESA has had the opportunity to really study this comet for many, many, many months. But this is an engineering activity. This is that huge step to be able to get really close to a comet, to really understand, potential gravitational perturbations, to be able to understand how firm these surfaces are. Now, Philae bounced around, but having a much larger system like Rosetta with the large antennas, if we're going to do sample return, which, as I mentioned, is going to be our next step in that particular area, it's stuff like this engineering milestone that we're going to see today that really gives us a lot more information and therefore more confidence that a mission for a sample return can be accomplished. So this is a really important day all the way around.
Absolutely. Well, Jim, thank you so much for joining us, and I know you're just as excited as everyone else there.
Absolutely. Thank
you.
All
right. Thank you. So we are just a few minutes away from the start of ESA's commentary. As we wait, Steve, just give us a sense of what this all means. This mission sort of gives the scientists ground truth, literally.
Yeah, and one of the objectives is to go inside of, or look inside of one of these pits. We heard about these goosebumps. Sometimes they're called dinosaur eggs, and so to be able to look inside the pit and get high resolution imagery. I could mention that we have been to comets before. We've even sort of landed on comets before. I'm thinking about the Deep Impact mission in particular.
And we have video. It's a very different scenario. Deep impact, we went at a much different speed.
Yeah, it's 20,000 times, 10 or 20,000 times the speed. So to call it a landing is sort of tongue-in-cheek, of course. Maybe 1 billion times the kinetic energy.
Right.
And so we've seen comets up close, but never for this long period of time.
So what's happening today is almost the opposite of deep impact, where it's going to be a soft landing, so to speak, onto a surface. And we have an image where we can see the landing spot that we could pull up.
Yeah,
it has
if
a
we can
circle
pull up this
on
image,
it.
there's a little red circle there, and just to the right there's a little shadow, and that's one of the pits, and that's what we really want to get a good look at. I think there's another image that shows even a higher resolution. There's just to the right of the center of the frame, there's a little elongated black area. That's the pit, and the center of the frame is the smooth area, which is the target. But the possible uncertainties in the landing are large enough that we could actually go inside the pit with this spacecraft.
How did they discover those pits? Was it from these flybys and these closer images that we were getting from Rosetta?
Sure. As we've gotten closer and closer to the comet, as the 2 years have unfolded, we get better and better resolution in the last several weeks. We've gotten much closer than ever before and been able to see these dinosaur eggs, these goosebumps inside the pits. Here now, we might look at some of the animations showing the very active environment. So these these images are enhanced in a way to show the gases and dust that are flowing away from this comet, and it actually has an atmosphere.
And that was one of the reasons why this mission stayed with the comet this long, was to be able to capture moments like this as it got closer to the sun and heated up and jets would eject.
Yeah, to get to the comet when it was, say, as far away as the asteroid belt, 3 times or 4 times the distance that the Earth is from the sun, so the comet's quiescent, and to follow it and stay with it and watch it as it becomes active, and then on the other side to follow it as it starts to become inactive and quiet. And so we've seen sort of all the seasons on Churyumov-Gerasimenko.
And that is critical. You're building that documentation about comets from start to finish, these key periods.
Yeah. As I mentioned before, getting these snapshots from flybys only tells you sort of an instantaneous. It's the difference between a still image and a video, and to be able to see, and we have seen this geology happening in real time, has answered questions and raised a lot of new questions about how these services are evolving.
All right, so what are you most looking forward to, since you study comets? What are you looking most forward to from this particular mission?
Well, one of the things is they want hang time. They want to come down as slowly as possible. And this was much like I was involved in the NEAR mission, where we also had a spacecraft with no landing gear, but we wanted to get down at the end of mission and take some really high resolution images. I'm looking for that money shot of a super high resolution of the comet.
I don't want to interrupt, but I hear that the ESA cometary is on its way. Let's go to Darmstadt, Germany.
Rosetta carries a metal plate on board with a message in 1,000 languages, hopefully to be found and deciphered by alien missions in the future, just like the Rosetta Stone was deciphered here on Earth. And of course, today the mission comes full circle, and as we get closer to the comet, we can gather even more data, so more highlights in a mission full of highlights. We'll talk about that with Rosetta scientists later on. We'll also get some close-up images shot en route as the spacecraft descends towards the comet. Now, the touchdown happens as we speak, some 718 million kilometers out in space. You've already noticed there was a time delay between Darmstadt and Guadalajara. Well, the time delay between Earth and 718 million kilometers in space is even bigger, 40 minutes. In the signal from the spacecraft down to Earth takes 40 minutes at the speed of light. So let's stick with Earth time and actually show you a bit around to show you what happens here. Because here in the main control room where we are right now, of course, we're surrounded by great flight operation experts, and they watch these large screens over there. They show the health of status of ESA's ground stations. Some show the data downlink of the Rosetta instrument, and we'll touch on that later as well. And one screen, that's the one in the middle, that shows us the downlink from the spacecraft. And that, of course, that chart will become crucial indicator for us today. We keep an eye on that spike for sure. And I know that the gentlemen that I've reached now here at the flight director's desk, they will certainly keep an eye on that spike over there. We can see here Andrea Accumazzo, the Rosetta flight director. We see Patrick Martin, the mission manager, and we see Sylvain Laudiot, the Rosetta spacecraft operation manager, in the middle between them. And down here as well, we see Paolo Ferri, the head of mission operations department. Good afternoon, gentlemen. Andrea Accumazzo, tell me, last night you've performed a final maneuver and directed the spacecraft from orbiting around the comet to actually go on a colliding course straight towards the comet. Did all of that work out?
Yes, right, that's correct. What we did last night was to do a maneuver to cancel the orbital velocity of Rosetta and direct it towards the comet. Now we're flying towards the comet. We have a most up-to-date estimate of the landing time is 11:19:11, and we are roughly 40 meters away from the target point. So this is an excellent performance of the maneuver.
Okay, well, we're used to excellent performances from Rosetta so far. Sylvain Laudiot, now since then, was there anything that you could have changed or change in terms of course or setting?
Good afternoon. So we did some changes a few hours ago. We optimized the pointing of the spacecraft on the way down for the last hour, and we also improved the Osiris commanding to better fit the expected impact time. Now it's too late. Impact is happening in 3 minutes.
Okay, and you're just standing here and you watch.
Correct.
But of course, in the meantime, because we spoke of that time delay, Patrick Martin, Rosetta now in the final hours of the flight, busy as a bee it's been. What do you receive right now from Rosetta?
Absolutely. The final descent is going well so far. We are in the last few minutes and we are in full science mode actually. Downlink of the science is going on right now with full priority to science, and stay tuned for the confirmation of the end of mission.
All right, and just briefly, Sylvain, how fast is Rosetta approaching the comet?
We'll be landing at 90 centimeters per second, and we're close to that speed right now.
Okay, 90 meters per second, that's about 3 kilometers an hour?
Centimeter per second, so it's half the speed of normal walking speed.
Very, very slow indeed. Well, thank you, gentlemen. Of course, we'll catch up with you later again. In the meantime, I'm walking very, very slowly so that the cameraman doesn't fall and stumble over the cable here. And of course, the spacecraft is approaching the comet at snail's pace, and it is busy. It is making scientific measurements, and it's taking pictures, images. And that is, of course, something we're very interested in, which is why we now cross over to a room where two teams are actually sitting, two science teams are sitting in order to take sort of the final measurements. And we cross over now to Holger Sirks. He is the principal investigator of the Osiris camera that brought us all the wonderful images we've seen so far of the comet surface in Coma. Holger, what's the latest? What can you share with us now?
Well, we are extremely excited. So the images are coming down like a charm. So let me show you what we are aiming for. So the green and the red dot, this is a 2014 image. Don't wonder about the quality. Are the pits we are aiming for. The landing spot is the blue one. So we're getting closer, and we were excited with the first image already coming down at 4 o'clock this night. This was the first image of the descent, taken at 16 kilometers with our narrow-angle camera. To give you a little context, this is the NAC view, so you certainly see this area here at the Hatmehit depression. This is what we are aiming for in these shots. So we are 15 kilometers, ever getting closer. This is a amazing view of the local terrain at good 8 kilometers altitude at close to 7 o'clock this morning. Going a step ahead, ever closer, good 5.6 kilometers, 8 o'clock 21 this morning. The first view now of the blue dot. We will land here, and we just learned from flight dynamics it's really there.
So
So expect really great stuff coming down. The pits were also in our view. Just this is the pit D. So we are looking already into this depression. And so from 5 kilometers, a lot details of the walls that we are after. And the last image I want to show is this. This is the detail of our pit D in high resolution from 2,500 meters distance. So it's really great, it's exciting, it's working like a charm.
It's the future home of Rosetta. Holger, just very, very briefly, after such a successful mission, why do we end it like this?
Well, it's all about science. So we want to see these images of the sidewalls because they give us clues about the origin of cometary nuclei. So that's why we do it, and that's why we get closer ever to exactly this spot that was decided by the science team of Rosetta.
All right, Holger Sierks, thank you so much for now. And of course, we look forward to many more pictures that you will show us in the course of this event. We'll get back to you. But in the meantime, I'm back here with Andrea Accomazzo, the flight director, who's just moved with me from one position, the main control room, to another. And of course, Andrea, this was quite a ride, the Rosetta mission, and there is an iconic picture of you that went all around the world. That was when Rosetta was woken up after 3 years of hibernation, and that event was already more than 2 years ago. It was an event, a mission full of challenges that you and your team had to face. I mean, really quite a ride.
Well, definitely. If you think about the Rosetta mission, was conceived in the middle of the 80s, when we knew very little about comets. We embarked on a trip of 10 years long in the solar system. We had to fly by planets to gain velocity to reach this comet with the right velocity. We flew by asteroids. We had to hibernate the spacecraft because we were flying so far away from the sun. Already the trip there was an adventure and a masterpiece of technology and engineering from all sides. All this for science.
All this for science, and you're a flight operator. What was the biggest problem? I mean, was it the fact that it was so far away, the distance, or the complexity of the hardware? What was it?
Well, during the design of the mission, I would say the distances Rosetta had to go through, definitely. We were close to the sun, far away from the sun, so different environments. The operations at the Comet was the second big challenge. It was much more challenging than anything else. Nobody had ever done anything like this, and we are leading, we are on the front edge there.
And have you learned anything from it? Has Ops learned a lot from that mission?
Well, we have done something, as I said, nobody had ever done. We are the only ones now capable of doing something like this. And this is an achievement not only for ESA, but for mankind. We can do something like this. And this is what we have to continue doing for the coming years. We have to go the next step. We have to go for sample return missions. If we want to protect our planet from asteroids, then this is what we have to be able to do.
After all the sleepless nights, I remember some sleepless nights with various events that we did together, and all those challenges, would you do it again?
Absolutely, yes, no doubt.
No doubt about that.
No, indeed.
Okay.
This is the most fantastic mission ever.
Indeed, Andrea Accomazzo, and you were part of this fantastic mission, still are flight director of Rosetta. Thank you so much.
Thank you.
And of course, yes, we all remember, of course, what an adventurous mission Rosetta was in all these years, and still for a few minutes. Let's take a look at some of the milestones.
Rosetta's journey began 12 years ago, and for the scientists behind the mission, it was even earlier. It took over 6 billion kilometres to get to the comet, using a gravitational kick from Mars and 3 planetary assists from Earth, circling the Sun almost 4 times. Rosetta studied asteroids Steins and Letitia along the way, monitored by ESA ground stations around the world. The spacecraft was put into hibernation in June 2011, spinning once every 60 seconds so that the solar panels could receive as much sunlight as possible. The alarm was set to wake up Rosetta on January the 20th, 2014. Within 6 weeks of the wake-up signal, all of Rosetta's 21 instruments have been activated, 11 on the orbiter, 10 on the lander. In May 2014, Rosetta put on the brakes and, together with a series of thruster burns, reduced the relative speed between the comet and the spacecraft to just 1 metre per second, and its separation from around 20 million kilometres to just 100 kilometres. The unusual shape of the comet became clear. Rosetta arrived at the comet on August the 6th, 2014, and shortly afterwards became the first spacecraft to orbit a comet. After a landing site was decided on the head of the duck-shaped comet, Rosetta released its Philae lander, and the 7-hour descent made history. As did the multiple bounces across the comet's surface. The first mission to make a controlled landing on a comet sent back its first spectacular images of the surface. After returning its science data, the lander's prime mission was over and it went into hibernation. Despite brief communications over the summer of 2015, its position was unknown until just a few weeks before the end of the mission. Rosetta's primary objective has always been to examine and monitor a comet and to see how it changes as it nears the Sun. And on the exact moment of perihelion, its closest approach to the Sun, Rosetta was watching. Rosetta is now heading out into the colder reaches of our solar system alongside the comet. Today's controlled descent onto the comet's surface is yet another first for the boldest cometary mission in history, advancing cometary science and our understanding of the universe.
And it's all about the science. We've heard that several times in the course of this mission. That's why with me now is Matt Taylor, Rosetta's project scientist at ESA, who overlooks a vast amount of science that was made and still is being made with the Rosetta mission. Matt, if you could pick of all the data that you and your team received, what was the most surprising finding?
That's a tough one to pick what we've been doing in the last couple of years. I think one of the big surprises was the shape of our duck. We've seen comets like that before, but this duck was striking. It was formed by two smaller comets colliding at low velocity. We then started to look deeper into it, this dark object covered in dust, full of organics. The implications are all over the place. The fact that we found water there, but it wasn't the same as Earth. But fundamentally important, going back to the organics again, this stuff could have been delivered by comets to the Earth and formed the ingredients for life, and how that started. It's brilliant.
And because science is always a bit scientific, sometimes too scientific for some people who follow it and are so interested in the Rosetta mission, we prepared a little video in order to just summarize some of the key findings. Then we talk again.
Yeah.
Rosetta's instruments, 11 on the orbiter, 10 on the lander, have transformed our understanding of cometary science. They've sniffed gases, collected particles, examined the comet across the electromagnetic spectrum, seen how it interacted with the solar wind, and scrutinised the comet's activity, tails and coma as it approached and moved away from the Sun, an unprecedented achievement. We had considered comets as dirty snowballs, covered in patches of ice, but Rosetta has meant we've had to rethink this picture due to a lack of strong evidence for ice on the comet's surface. Instead, the ice is buried, covered by a layer of dust. This dust layer means that the comet is very dark, reflecting only a small fraction of the light that falls on it. The Vertis instrument, a visible and infrared spectrometer, revealed how water is transported from within the comet to its surface via sublimation, where water changes from ice to a gas without a liquid phase. This process provides a frost layer which is replenished each comet rotation. The OSIRIS camera and Vertis have also found more persistent ice deposits on the surface in regions near cliff-like structures. It may look rocky, but the comet is so light and porous it could float on water, with surface temperatures falling below -100 degrees C. Gases streaming from the comet include hydrogen sulfide and methane, and there are pits containing walls hundreds of metres high. These walls revealed layers that helped scientists determine that the comet was formed by a slow collision between two smaller comets. It has no magnetic field, and gases detected include molecular oxygen, hydrogen sulfide, and for the first time found on a comet, argon. The two Rosina mass spectrometers revealed that comets like 67P may not have been a dominant source of water for our planet in the early solar system, because its water has a different isotopic ratio. But organic molecules discovered at Comet 67P, such as the amino acid glycine, tell us that comets could have played a role in the emergence of life on Earth.
And that is indeed exciting. Matt Taylor, Rosetta's project scientist at ESA. What does all this mean? Has any of the data really changed our understanding of how the solar system came about?
Yeah, Rosetta's blown it all open. It's made us have to change our ideas of what comets are, where they came from, and the implications of how the solar system formed and how we got to where we are today. And we've only, like Philae, just scratched the surface. And it's important to note, Rosetta mission is both the lander and the orbiter. Together, they have made it possible to do the science, to make the breakthroughs that we have. And we have only just scratched the surface. We have decades of work to do on this data. So the spacecraft may end, but the science will continue. That's what we were here. That's what we're here for. That's what this mission was for.
And that's a beautiful message, especially on a day like today. Matt Taylor.
A sad day.
Yeah,
but a happy day.
Yeah, exactly. A bit of both. There's always two sides to every coin. Matt Taylor, thank you so much. And by the way, just to give you an idea about the huge harvest of science that Rosetta has delivered there, Rosetta has triggered a total of 672 science papers since the launch, just 119 this year alone, with another 50 in the pipeline. So, as we just heard from Matt Taylor, it is just beginning, the science part of it. And talking of science, it's time to go back to Holger Sirks, whose team is processing the images that the spacecraft is taking during the descent. Rosetta is about 30 minutes away from touchdown right now. So, Holger, I'm sure you've got some new and amazing pictures for us.
Well, it's a bit hectic here these minutes. So we are at a good 2 kilometers altitude now. So what we prepared is a view by the wide-angle camera, so a wide-angle shot of this landing area. The pit D over here, the pit E over there. Landing will happen there in the upper right. So that's a cool overview. So we focus right now on the main part of pit D. And zooming in with our telecamera, so this is what we see. So the side walls of this pit already. So with the structures, thermally processed, goose-bumped, whatsoever. So we will work on these images for the next year. So we get great detail down of the whole area as expected. So imagine we are more than 700 million kilometers away. We have to compress those images to the utmost, so 1/20, so they are not as crisp anymore as we are used to have them. But it's great detail and good science to be expected from there.
Okay, brilliant. Holger, thank you so much for this. And obviously, we won't let you go before all this is over today. We'll come back to you later again. But I would like to turn now to the other team that's sharing the room with you. And there we should very soon see Katrin Altweg. She is the principal investigator of the Rosina instrument, and that is receiving data from Rosetta right now as we speak. I mean, 7 instruments on board of Rosetta. Of those, 11 are still working, very, very busy. And if we remember, the Rosina instrument brought a breakthrough in science in deciphering the chemical composition of the comet. Katrin Altweg is from the University in Bern, and hopefully she can hear me now, and hopefully she can tell us a bit and comment a bit on the kind of data that she receives from Rosetta.
I have still 2 of the Rosina sensors on. That's the mass spectrometer DFMS, and it's also the COPS sensor with 2 gauges, the NUC gauge and the RAM gauge. What you see here is the pressure. So it's the density in the atmosphere of the comet, and it rises and rises since this morning. We are still at not very high pressures. I expect it to rise by another factor 2 before we land. From these curves, we will really get a cut through the whole atmosphere of the comet. We will understand how dust is accelerated. We will see all the regions which were postulated by the modelers, and then constrain their models with these last measurements, and I think it's a unique opportunity to do that.
Wow. Katrin Altweg, thank you so much. Unique opportunity indeed. Actually, let's sum this up. I mean, this part of the mission, the fact that Rosetta is landing on the comet, that was never really planned. That was never envisaged in the first place. It was a decision by the scientists in the end, wanting to make the best use of those wonderful instruments on board, instruments like the Osiris camera or Rosina, as the Rosetta spacecraft gets so close to the comet, a risk that one could not have taken earlier. And so this is wonderful. And we see, of course, in the course of now this broadcast, also the images and the results of all the data that we receive from the spacecraft in those last minutes. Actually, talking of minutes, we have about 27 minutes to go until we get the signal that Rosetta touched down. And I think this is a good moment to revisit another major highlight in this mission. And that, of course, was the landing of little Philae in November 2014. And it was a short-lived, but a very, very, very successful mission. The data that Philae managed to gather was quite impressive. Take a look.
On the 12th of November 2014, Rosetta's Philae lander made history by performing the first ever controlled landing on a comet. The lander then sent back the first ever images from the surface of a comet and undertook 60 hours of science. It wasn't all plain sailing. The harpoons didn't fire on landing, and as Philae wasn't anchored, it bounced across the surface of the comet. When the lander finally came to rest, its position meant Philae couldn't drill into the soil to collect samples for the different instruments. Instead, they went into sniffing mode, analysing the gases surrounding the comet and from scattered dust grains. But Philae completed 80% of its planned science, with measurements from multiple landings across several locations providing unexpected benefits. The bounces allowed scientists to compare measurements across the comet of, for example, the comet nucleus's magnetic field. By working with the orbiter, Philae has helped scientists understand how the comet's interior is formed. Radio waves were transmitted between the lander and orbiter to see how they were reflected and transmitted through the comet's nucleus. The smaller lobe where Philae landed was found to be fairly homogeneous. This sort of information, especially knowing how hard the surface is, will be crucial for any future missions involving a comet sample return. Philae went into hibernation after completing its science mission. Apart from several brief periods of contact over the summer of 2015, the lander has been silent, position unknown. And then, less than a month before the end of the mission, Rosetta found Philae, on its side, wedged in a dark crack of the comet. It's now time to say farewell to both the orbiter and its lander, before Rosetta joins Philae for its final resting place on the comet's surface.
And we'll talk to the man who is responsible that we could find Philae in just a moment. But first, I would like to cross over to our big conference room, which isn't far away from here, where Jocelyne Landau-Constantin, she's ESA's head of communications office, is on stage and surrounded by a lot of mission engineers, VIPs. Jocelyne, can you hear me? Tell us what's happening.
We are hearing you loud and clear, and I have with me Jean-Pierre, and I'm going to ask you the only question that is difficult. What is the best result of Philae?
Jocelyn, supposedly I would ask you what are the best moments in your life. You would not be able to pick one, right?
Yes, now.
That's
right
exactly
now.
where we are. Philae was so fruitful, successful, that it's difficult, barely I can extract one. Maybe the first thing I would say that Philae within Rosetta has entirely changed our view of what a comet is. Comet is not an icy ball with molecules and grains inside. Comet have been built with a matrix of organic matter formed during the collapse of the clouds through a chemistry which is so important and complex that probably you have all the ingredients in this comet that we see on our images that when immersed in the oceans probably led life to emerge. But beyond the understanding of what a comet is, Philae within Rosetta has also tell us all the processes that really shape the solar system to drive the diversity in which we are now. And it's really changing paradigms. In particular, that to me was important. What is the transition from inert to living spaces? And this changed a lot of things from habitability, for example, and that paved the route for the new missions we are in now. The exploration of Mars, the small bodies, Europas, Ganymede, exoplanets. We have now to address questions which are entirely different from those we had prior for Philae and Rosetta to be there. So I think we couldn't dream of a more successful mission.
Thank you very much, Jean-Pierre. So, ladies and gentlemen, decision makers, there is room for another mission, obviously,
Absolutely.
and many more missions.
For many more, yes.
Thank you very much. We are going to go back to the control room.
All right, Jocelyn, I can hear you. And more missions, we like to hear that. But let's stick with the one that we're still covering at the moment, the Rosetta mission. And Philae, of course, was a big, big part of it. Next to me is Lawrence O'Rourke. He's been the search coordinator for Philae in the past 2 years. It was your persistence, I said earlier, that made it possible to find Philae. Tell us about it.
Indeed, it wasn't an easy job. I mean, already after the landing, we had a very good idea where it actually had finally landed. It landed in an area which had a lot of rocks, very full of ice and very dark and not much illumination. And in the end, as we started getting closer this year, we managed to find some candidates, some locations which looked like the lander, and you can see this in the image which we're showing now, hopefully, which there's a blue one and a red one.
And which one was it?
It was the red one, and the red one was already identified as our favourite. It was defined as the best candidate from June of last year, and we spent a lot of time this year trying to get images of this red candidate. But the problem is it's been between a rock and a hard place. It's got a cliff on one side, it's got an angled rock on the other side. Part of the rock, the highest point, is the height of a 20-story building. You're trying to look over this to try to get the lander, and in May and June we managed to acquire some images to see the light shining in the darkness. We got something which certainly gave us confidence. We had the lander, but also a lot of ice in the area, and we needed to get a really good image to confirm it.
And the confirmation came on September the 2nd, not that long ago.
Absolutely, and what a beautiful image it is.
Yeah.
It's so rewarding for the team. It was a big team across many projects, across the Rosetta project, but across many teams, and it was so great. But what's important is the fact we found it. We found it, and it gives context. It gives local context for the science that was the fabulous science produced by Philae. I was delighted, and it's really great to have found it before the end of the mission.
I just wanted to say, Lawrence O'Rourke, thank you so much to you and your team that you did find Philae. Made us all very happy. Thank you. Well, talking of images, we just saw great images. Of course, this is the moment where we want to go back to Holger Sirks, who has his Osiris camera, the eye of the camera on the Comet as Rosetta is approaching it fast. Holger, what's the exact altitude now? How do we know that?
Well, we are already at about 1,000 meters, so closer than ever before. So we haven't processed those images yet, so they will come in a very few minutes. So what we have built up here is a mosaic of the marred raster with the narrow-angle camera. So don't wonder about the resolution. You see the 5x4 images put together not nicely just as they came down. So you see one pit over here, the deep pit over there, and the expected landing site over there. So we've got all those imageries and all those images at high res down, and we will do a better job in stitching them. So if we now looked into the detail of the pit D, with the slightly slewing spacecraft to the best resolution of the narrow-angle camera, this is what you see on the ground of that pit.
Okay.
So the ground, the side, the wall, lots of stuff that just fell off, broke off cliff. So it's great. It's coming down. And it's super duper. I lost my clip.
That's why you can't hear me,
so
Holger.
I can't hear you anymore.
That's why you can't hear me. Then I'm not going to ask you the next question. I'll ask you the next time when we go over there. And I'm staying now with the gentleman who is right next to me now in the main control room. Of course, we know him, Mark McCaughrean, the ESA Senior Science Advisor to the Director of Science. And we've always been wondering throughout those years why Rosetta, why this mission has managed to get such a huge following in the media and in the general public. Why do you think that is?
I think there's two main parts to that story, really. One is that it's a mission that's about us as human beings. It's about our birthplace in the solar system. It's about the planet Earth and how water and life may have come here. So I think obviously people can associate with that. But it's a journey. There's Rosetta and Philae, 10 years through the solar system. Our protagonists, they've had their ups and downs. They've had their bumps. They've had their bounces. We know that. And, of course, in this room, when Philae's battery ran out in 2014, emotion around the world, social media was just enormous. And I think today we've been working with lots of people, listening to people, and they're very sad today. But I think they really understand how proud we are and how proud they should be that we've really pulled this mission off.
Exactly. And I think some of those voices we will hopefully be able to see on tweets. Because do you remember during the landing of Philae, they were something like 10 tweets a second coming in? And I think we don't do that badly today either. There is a hashtag, Twitter hashtag, it's Comet landing, obviously. And there we see some tweets, but they're not, the resolution is not brilliant for me right now. So is there a chance that Rosetta will bounce? Mark, can you tell us?
Well, it's a little bit like the old story about a tree falling over in the forest. If there's nobody there to hear it, will you actually? Does it make a sound? It may well bounce. The predictions are it's a certain possibility, but we won't know.
We won't know.
Because we turn off when we touch the surface.
Yeah.
We may have the slightest information. But yes, it's a good possibility.
I like to imagine it bounces towards Philae and then they are reunited again.
It's got a long way to go for it to do that. But,
it's bigger.
This is space. Anything can happen out there.
Okay, Mark McCogran there. Thank you so much.
Thank you.
It's time again to cross over to the ESA conference room because Jocelyn, who we've just seen, she is surrounded by some mission veterans. They've been there forever, certainly with the Rosetta mission. John Elwood, Gerhard Schwem, Manfred Warhaut and Alan Smith, and they all have something to say, I believe.
Thank you. Alan should join us as well, and Gerhard, he's probably surrounded by a lot of media asking plenty of questions. They're all coming. They're colleagues, they are friends. They've been with the mission for a very, very long time. And I'm going to start with Gerhard. Gerhard, you started in the 80s with this mission. And what is the first thing that comes to your mind? We're very close to the end. Did you think it would have been such a successful mission?
No, when we started, I think a lot of people thought we are crazy to go in such an ambitious mission. And for me today, I'm just proud that the project is coming to an end. And we were ambitious. I think we delivered what we wanted to do. We had high hopes. And today, I think we got out more of this mission than we ever thought. And it's a great day. And I think with all these happy scientists, we must have done the right thing.
John, you were the project manager. Was it a piece of cake?
Absolutely. I mean, when I look about the results that have come out in the last 2 years and then think about the 2 years that happened before we actually launched the spacecraft, it's absolutely amazing the number of hours, the night shifts that industry put in to get this spacecraft to the launch ready to go. In fact, it was ready to go a year early, but it's absolutely amazing to think back on that, and this obviously brings back all those memories, and what a fantastic way to finish the mission.
Manfred, this is finito, by the end.
Yeah, I must say today I'm a bit irritating. Normally I wait a signal to appear, like 2.5 years ago, when we were waiting for the wake-up. And today we wait for the signal to disappear, which is then demarking basically the end of the Rosetta mission. But nevertheless, I can tell you on this mission was always big excitement and a lot of success and a lot of people who made it happen.
Alan, you were flight director. So it all
yes,
started with...
12 years ago I was a flight director and sent Rosetta on its way. And I must say I've been very, very proud of the accomplishments of the whole team who've looked after it, and also what the mission has delivered. And today is one of the strangest days ever in this conference room, where there's no stress. It's can be quiet. Well done, Rosetta and everybody.
Thank you, and back to the control room.
Very much, Jocelyn, and a warm hello to all the veterans over there. Wonderful pictures there in the background. I have here with me now ESA's Director of Science, Álvaro Jiménez. We just said there's no big agitation in the room over there, but Rosetta as a mission, of course, was really, really complex. One of the greatest missions ESA has performed so far. It raised the bar. Have you got anything similar or even bigger in the pipeline already?
Well, of course, we want to do difficult things. That is what we enjoy. This is a challenge, and scientists always want challenges. Otherwise, we have no fun. So we have to really do difficult things, and we are happy with the Rosetta mission. We are preparing now the landing of ExoMars in the coming days, ExoMars 2016, and we are also preparing a new mission to Mercury. That's Bepi Colombo, that will be unique in its performance, and also a mission to the icy moons of Jupiter, which will be for the first time to put a mission orbiting one of the moons of an outer planet, that is Ganymede.
Okay, so you keep everybody here very busy. But all these missions are getting very complex and very expensive. Are those agencies all working together?
Well, that's, of course, the only way to go ahead. We need new challenging missions, and we have to do that in cooperation. We have large corporations, of course, with traditional partners like NASA, but also with JAXA, with Russia, with Japan, with China. This is the way to do science, and science is the glue for cooperation, because scientists are naturally international. They are there for science, and this is international, and we have to use that as a driver for new mission and new cooperation. We are very happy on this cooperation to go on.
All right, Álvaro Jiménez, thank you so much. And of course, we have about 8 minutes to go until touchdown. That's high time for us to go back to Holger Sirks to see if he has another picture for us.
So I've got just one. And a great one, but to lead you in once more. So this is a context image. So that's the end of the raster, the slewing around the pit D, and from here we'll adjourn for the landing of Rosetta and the final meters. So just to get you a picture also of what the property will be at the very last moment. The closer we get, the smaller the area we image will be. So the image taken at good 1,000 meters at 2 centimeters per pixel is here. You see on one end the ground, the bottom of the pit D, the shadow of the wall, and the upper part, so all the landscape around the pit D. This is really great. It's the first time ever the comet is imaged at this resolution.
Okay, Holger, thank you so much. Of course, as the spacecraft gets closer and closer, the pictures will become more and more blurry, but we do look forward to the very last one that you will share with us later on. But in the meantime, 7 minutes to go. We have to speak to one gentleman who is next to me, the missions or head of the missions operations department, Paolo Ferri. Now, this is a very strange moment, quiet somewhat here in the main control room. What's going through your mind after all these years taking care of Rosetta?
Yeah, it's always quiet when it's a critical phase, but this is a special one. I think everybody is very sad. On the other hand, the mission end had to come, and I think it's a spectacular way to do it. So we are quite convinced it was the right thing to do.
How will we know that it landed?
Well, for sure, we expect to lose the signal because we programmed the spacecraft such that it switches off the transmitter once it detects somehow that something went wrong and something touched down. We hope to see in the very last seconds of telemetry to see some clear indication, for example, movements of the body of the spacecraft that show that really it has touched down. Rosetta was not designed for touchdown, so we do not have specific sensors for that.
And this is then the end?
That will be definitely the end. We've programmed the spacecraft such that it will not be possible to reactivate it again. We wanted a clean end, and that's the way we hope it's going to happen.
That's the way. And because it's an emotional moment, even though we want a clean end, Paolo Ferri, thank you very much. With some less than 6 minutes to go, I think this is a very good moment to stop commenting on anything and just remain silent and let you and the teams watch the touchdown unfold. We'll be back later.
all stations on the briefing room just have lost the signal at the expected time. So we'll have a fast landing performance from flight dynamics. So we'll be listening for the signal from Rosetta for another 24 hours, but we don't expect any. And so this is the end of the Rosetta mission. Thank you and goodbye.
Here is now Patrick Martin, the Rosetta mission.
Ladies and gentlemen,
Okay.
I invite you
This
to
is
sit
it.
down again. We need to
I
listen
can
to the
confirm
last statement.
the full success of the descent of Rosetta. I declare the mission operations ended for Rosetta. This is the culmination of
And you are watching live coverage on NASA TV. This is coverage coming to us from the European Space Operations Center in Darmstadt, Germany, where we have just seen the end of signal from Rosetta, and thereby indicating impact and end of mission for the Rosetta team.
Now we have the mission manager from Rosetta here with us, Patrick Martin.
Hello, this is it. I can announce the full success of this historic descent of Rosetta towards 67P, and I declare hereby the mission operations ended for Rosetta. This is a culmination of tremendous scientific and technical success for this mission, thanks to the involvement and the superb job of all scientists and engineers who contributed to build, design, and operate the spacecraft and its payload. In particular, I want to thank all the instrument team on board the orbiter and the lander, also the science operations team at ESA, the flight controllers, the flight dynamics team here at ESA, and of course our American partners. Flying to a comet and around a comet for over 2 years, as close as a few kilometers and more than 500 million kilometers from Earth, is a challenge, and we've done it. And this tells you that we've got the right people here, and the best people you can get to do this job, and we are very proud here. Of course, I want to thank the family who bear with us, because people spent long nights, long weekends, some of them their whole career. So thanks to the families as well. ESA's Rosetta mission was inspiring to many, was historic, was pioneering, and revolutionizing at the moment how we understand comets and the solar system. So to finish now, the Rosetta Stone was originally located in size, and we shall name the impact point as such, so that we can finally say that Rosetta has come home to size. Farewell, Rosetta. You've done the job. That was space science at its best. Thank you.
The flight of Rosetta has to be really perfect. We have a very, very long journey.
Many emotional days, and then we came to this wake up 10 years later.
We're there, we've arrived. 10 years we've been in the car waiting to get to scientific Disneyland. The big roller coaster waits us in November. You know, that's the scary ride to go on.
We definitely confirm that the lander is on the surface.
How audacious! How unbelievable! To land on a comet. It's a big moment for all of us. It's a conclusion of many years of planning. There's an engineering side, there's the financial side, and there's also the guts that some people have had to push the mission to adapt to circumstances, to setbacks. And I have several of them, with me today. I'm going to start with Rolf Densing. He's the Director of Operations. Rolf, what is your feeling now? Sad, half good?
Well, I personally came to the mission quite late, so there are certainly a lot of people that contributed more than myself, but still, as Director of Operations and Head of ESOC, I feel very proud on our teams for pulling this off. This was great. So I still take the liberty to be very proud today, and best way to fight off depression is to look ahead. There's life beyond Rosetta. As great as it was, we will be back for landing on Mars on October the 19th.
Thank you. We go next to Michel Menking. Michel, good job for manufacturing, good job for cooperation.
I think first of all, you witnesses, I think we have built a very good vehicle. But coming back to that, Airbus Defence and Space was a prime contractor of Rosetta, but we have a talk about the company, that's not true. Because at the end, it's really a huge industrial team. I'm talking for 96 companies which were headed by Airbus Defence and Space, coming out of 16 countries. So first of all, it's really a European mission, what we have seen here. And as in science, without cooperation, this is not possible to get these kind of achievements. I would like to accomplish a little bit what Rolf said, considering what is after Rosetta. Besides all the scientific work, and I can only confirm, I'm sure that there's a lot to do to get all the data and at the end to make the investigation of that data, we should not forget Rosetta was also kind of technology test bed. We did a lot of first with Rosetta, which we have seen and which we'll see in other missions. For example, Venus Express, Mars Express was based on the experience which we got out of Rosetta. And even if you look to today, Gaia, with which we are mapping the universe with 1.6 billion stars. The technological baseline is based on Rosetta, which was the first application, for example, of silicon carbide. And last not least, really supporting UFR into the future, JUICE will use a lot of also operational subjects with hibernation, which gives some tension to us, which will be used also for JUICE in the future for these kind of scientific missions and to make them a success.
Jeff Yoder is coming from NASA. There's no big science without cooperation.
First, I would really like to, on behalf of the entire NASA family, congratulate ESA and all the partners for this Rosetta mission and this historic event. The partnership that we have with ESA on Rosetta mission is just a start of, or an example of the great partnerships we have with ESA and partnerships that we intend to have in the future.
Thank you, Jeff. All the gray hairs are on Rosetta. David Southwood, he was the former director of science, and it has accompanied a long part of his career at ESA. David.
Yes, I can show you the scars, but it's all over. And but what I want to say, I was delighted to hear about the cooperation with the Americans. That's terrific. But I'm going to say this with an English accent. This was European through and through. It was a European launch. It was European operated. And we've just finished in a gentle European approach to comets. You do it your way, we do it our way.
Professor Bonnet was your predecessor, David, and what does it mean today?
Today it's a very sad moment for me. It's like cosmic euthanasia. You see, you just pull the plug. But this mission has been a dream. Since the very beginning in 1984, when the scientists sent the first proposal for a mission to a comet or an asteroid. And we have conducted this mission for so many years. But it has not always been a bed of roses, contrary to what John Elwood said, because one constraint which I gave to the engineers and the scientists from the beginning is that this mission could not cost more than 400 million to ESA. And if you take this to 2014-15, this 400 million translates into 1.2 billion. So not counting the cost of the experiments and of Philae. So we did better than the 400 million. It's also a fairy tale. The nice Rosetta is now on the nucleus. It's a sleeping beauty. Let me wish that maybe a charming prince, a Prince Charming, will come one day, maybe from ESA or from NASA, to wake it up. So let's hope.
The last speaker, but not the least, is one of the fathers of Philae lander. Bernd Feuerbauer was working at DLR at that time. Bernd, I remember a time where we spent a few hours selecting the name of Philae, but that was the very simple part of it.
One of the most simple procedures. I hope you forgive me if I talk about Philae. Philae has been such a brave little boy sitting up there in a ravine in a bit unfortunate position, but still doing fantastic science. It sent down a lot of excellent data down to the ground, and it will give the scientists for years to work. It is so nice to see that Rosetta and Philae together really have changed the paradigm of our understanding of life, of the Earth, of the origin of the planetary system. And I think this is a great achievement, and we can all be very, very proud about it.
Thank you very much.
we will have a surprise message. Mrs. Tupris, the Secretary of State in charge of the coordination of aerospace and space in Germany, could not be with us, but she did send us a message. So I'm waiting for this to be shown.
Wake up, Rosetta. That's history. It's now time to say, sleep well, Rosetta. Rosetta is unique, Rosetta is visionary, and it's a true European project. Over 20 years ago, extraordinary trust was given to European engineers and scientists. Today, we reap the fruits. Spaceflight has proved that it can set the pace for new developments in technology. And thanks to Rosetta's discoveries, the human race has learned more about space and about what makes our planet so special. I'm proud to say that Germany made major contributions to this European mission. I congratulate the ESA and the DLR and would like to thank everyone involved in the mission.
For one of the mission veterans on stage in the conference room who spoke in British accent particularly. I'm sure you know this. Good night, sweet prince. May flights of angels sing thee to thy rest. That I could not get out of my head ever since I knew that this final day for the Rosetta mission would come. And now that we know that Rosetta is joining Philae on the Comet again, maybe this angel choir sings songs composed by Vangelis, because he's actually the one who composed a special suite for Rosetta. That's how important it is. So, the Rosetta mission has come to an end after 4,595 days in space. The orbiter touched down and terminated the mission at exactly 11 hours, 19 minutes and 19 seconds UTC. And in these final hours of the mission, Rosetta was extremely busy gathering lots of data and images. And one of the scientists actually still owes us some data and image. Holger Sirks over there in the little working room. Holger, show us.
Here I am. So it's a little busy over here. So we're getting a chunk of images in high cadence. It's great. It's very crude raw data, so not deconvolved. It was very hectic over here. So this is what we see on our screens without any post-processing. This is the NAC image from 750 meters taken at 1022. It's a cropped image. It's a little out of focus, so we'll have to do our magic and deconvolution. Now we go further down. 590 meters, again the narrow angle camera, again the crop, so you see all the detailed structures on the surface that we are after. We are talking 1 centimeter per pixel here. So we are there.
And this is the final picture.
No. I want to browse you. I want to bring you down to the surface now. This is the WAC camera. So we had to flip from the narrow angle camera to the wide angle camera, and that's the broad field. This is what we get in return. Broad field by the wide angle, 1600 by 640 pixel, 360 meter above ground. A gravel field with great resolution. This will keep us busy. Imagine you want to count boulders. Ever getting closer. This is the famous F11 we wanted to try out. No glass in the beam, and getting sharper the closer we get. This is minus 10 seconds, not really processed yet. So you see the stuff on the ground. It's amazing. So this is about 10 meters above ground. This is about 5 meters above ground, and landed. And so I want to dedicate these images to the great engineering team that made Rosetta happen, the great engineering team that made Osiris happen, the great mission team here at at Darmstadt, in the great mission team at ESTEC, the great mission team at ESA. So they all made it happen. It's their images, it's heritage, the legacy of Rosetta. So
and I ask you again, Holger, this is the last picture Rosetta sent?
This is the last
Wow.
picture we have gotten down from Rosetta.
Wow, that's really, really, really in focus. Amazing. Holger
Well-
Seox, thank you so much.
Okay.
You and your team, thank you so much for keeping us up to speed there visually as well. Well, and we're almost coming to the end of this broadcast. You've seen emotions were running high here in the main control room and also in the conference room with Jocelyn Lando, Constantine and all the other veterans. Of course, for all of them, this was a substantial part of their life. Congratulations to all of them and thank all of them for making this mission possible and bringing it to us. But before we close, I have one more message for you. Please bear with me, because we heard so often that it's all about science and it's also about inspiring people. Now, this mission truly has inspired people around the globe. And this message that we got here from a young woman from Poland really encapsulates this best. I'll just read it out to you. Listen. I fell in love with astronomy at the age of 6. I asked Santa to get me a telescope for Christmas, and I've been spending my pocket money on books. Everyone kept telling me I couldn't become a scientist because people like me just don't become scientists. I'd have to be born in the US and so on. Now, I've been a couple of years later, I've learned about the Rosetta mission and I've been following its progress, and I was moved seeing tears on the faces of ESA personnel when the probe sent its signal to Earth. I was proud of what Europe has achieved, and I thought that if we can land a probe on a comet dashing through space, why would my dream of becoming a scientist remain a fantasy? ESA inspired me, and the Rosetta mission launched me towards starting studying physics. There you are, ladies and gentlemen. It is the next generation in the making. The Rosetta mission may have ended, but the science is just beginning. And listening to this, it just keeps going on and on and on. And with that thought, I would like to say goodbye. This brings us to the end of our live broadcast, straight from the European Space Operations Center here in Darmstadt. I'm Monica Jones. It was a great pleasure to bring you this historic event. And of course, do stay tuned to ESA's social media and webpage for the latest updates. Thanks so much for spending your time with us. Have a good day.
Finally, Rosetta's big day had come. It was time for her to join Philae.
And welcome back. That concludes ESA's commentary for the end of the Rosetta mission. This is a tremendous success for ESA, and NASA, of course, salutes this success because what's left behind is a treasure trove of science that the entire world will be able to share. The dramatic ending took place at about 1:19 p.m., close to 1:20 Central European Time, about 4:19 a.m. Pacific, and 7:19 Eastern. Before we go, we wanted to do a little recap and hear from American members, as well as Steve Chesley, our senior research scientist who works with near-Earth objects every day. Give us a recap of what took place, the final signal that we were watching.
Right, what we saw just a few moments ago was there was a video of the signal, and there was the center spike on that monitor, and we were waiting for that to collapse, essentially, which would be the indication that Rosetta had touched down, its attitude had gone off kilter, and the antenna was no longer pointed at Earth, and at that point also the Rosetta spacecraft would shut down to avoid any radio interference with other space missions, and so that means that Rosetta is gone, it's gone to sleep, but at the same time we got these spectacular images that have been coming down as we've seen in the ESA format.
And what can you see? We've gotten a couple of printouts. What were you able to kind of draw from some of these images? And not all of them are high resolution either, but you could see certain things.
Yeah, if we I don't know if we can pull up. There's an image from 8.9 kilometers that actually shows there's a in the lower left corner. Well, let's see. There it is. In the lower left corner, there's an edge of one of the pits, and we can just rotate to or flip to the one at 5.8 kilometers. I think that's pretty much the next image in the descent. And now you can see the full pit, and you can see the walls on the sort of the bottom center of the image, and this debris at the bottom of the pit that appears to be erosion and collapsing into the pit. These images have a resolution of about 10 centimeters per pixel, roughly. That means that they'll be able to see things in those images about the size of a volleyball.
Wow.
And as we saw at the end, that they got all the way down to pictures at 5 or 10 meters off the surface. There will be blurring, but I think it's very likely that we'll get millimeter or several millimeter quality images from those final shots.
Well, one person who will be especially excited about this is Bonnie Barati. She is the U.S. project scientist. Bonnie is standing by right now. And Bonnie, let's get your reaction to what took place.
Well, it was quite surprisingly a subdued moment. You know, I've been at other encounters and events, and usually there's a lot of hoopla. And at this one, there was really a lot of not quite sadness, because we have all that data to analyze, but people were a lot more subdued than I've seen, for example, at the Pluto encounter or the orbit insertion for Cassini. People were really sad that this spacecraft's life was going to end.
Well, can you give us an overview so far of some of the biggest science findings from Rosetta?
Well, I think that the biggest one is that we're pretty certain, about as certain as you can get in science, that we really are looking back at the formation period of the solar system. The two small bodies that make up this comet are almost certainly, and we call them planetesimals, are almost certainly primordial, dating from the early phases of the solar system. They don't seem to be processed in any way. These are truly the building blocks from which the planets were formed. The other thing that I find most interesting, I think most significant, is the amount of organic molecules that we found on Rosetta, including an amino acid. Scientists think that you can't form organic molecules, the building blocks of life, in the inner solar system where the Earth is, because it's just too hot. They form in the outer regions of the solar system, these complex molecules that have carbon, hydrogen, oxygen, nitrogen, potassium, the things that life needs to form and be sustained. It's believed that they are formed in the outer solar system and brought into the Earth by comets. And we saw many of these molecules on 67P, including glycine, the amino acid.
And Bonnie, this is Steve. I'm wondering if you could talk about the pits and these, I guess they're called the dinosaur eggs, which is probably not actually about paleontology. These few meter-sized spheroids that are on the walls of the pits. What is the scientific understanding of the importance of those at the moment?
Well, they're very important. I think the reason for that is prior to this mission, our whole ideas about the formation of the solar system, how the planets formed, was very hand-wavy. I mean, it's like, well, here's this cloud of gas and dust, it collapses, and then somehow, miraculously, these planetesimals, these things that are basically the comet that we just investigated, form. We never really knew how they form. It looks like these dinosaur eggs are the small particles, and as you said, they're a few meters wide. They're conglomerations of the dust from the interstellar cloud that collapsed, and they form these dinosaur eggs, these boulders that gravitate and then get bigger and bigger and finally form a planetesimal. So this planetesimal, we believe, is made up of these smaller objects, you could call them smaller planetesimals, that we have jokingly called dinosaur eggs. So I think that's a great discovery, that we kind of see the progression of how these planetesimals were put together.
So, Bonnie, I'm sure folks are elated and excited, and you will have scientific data to peruse and study for decades to come. Thank you so much for joining us.
Thank you. Thank you.
And Steve, let's talk a little bit about this. We're standing by to see if some other members of the American team will be able to show up at the ESOC. You were talking about the fact that this particular comet is actually two pieces that, and they mentioned it also in the commentary at ESA, that there are two that have come together. And you mentioned that they may break apart and come together again.
Yeah, I can mention one of the earliest ideas, which I think has been substantially ruled out, is that this used to be something much larger, and this neck somehow was formed by erosion. But if you look and study these images carefully, as the scientists have done, what they find is that these are sort of like two different onions with their own separate layers. And so they couldn't have formed in the way they are. They're two small planetesimals that came together at very low speed, maybe a meter or a few meters per second when they came into contact in the early days of the solar system. And they're held together very, very weakly. And as these comets change their rotation rate from all those jets that are pushing on it, that spin up faster and faster, they can actually come apart, but not escape and circulate chaotically until they come back into contact in another configuration.
All right. Well, we've just been told that we have another guest over at ESOC, and in just a moment we'll be standing by, and he's being mic'd up as we speak. Let's talk a little bit about this. I mean, what are the big call-outs that you're seeing so far? Is it mainly the imagery that we're seeing, or is it the fact that we had all the instruments going down and we were taking in data all the way down to the very end?
So we're visual creatures, right? And those images are the most amazing things to look at. But I would say that as much as the images provide a lot of important scientific information, all these other instruments, the sniffers, the spectrometers, the microwave Miro instrument from JPL. So these are going to provide as much, probably more information, but it's just not as easy to digest in a quick situation. So the scientists are going to be studying this data for, as we've said, for years to get their arms around what this comet's doing.
All right. I've just been told in my ear that we have over at ESOC the Associate Administrator for NASA's Science Mission Director, Jeff Yoder, standing by. Jeff, are you there?
I am.
So what was it like for you watching the end of this mission? This should be a big tribute to international cooperation.
This is an excellent testament to international cooperation. If we look at the Rosetta mission, the partnerships, the instruments that NASA and our partners have provided, communications. This is just a testament to a good working relationship with partnerships, and how we look to in the future continue on this partnership.
What do you see ahead because of this success? Do you sense that there will be more and more?
Oh, I do. So we have upcoming missions. Example, the James Webb Space Telescope launch in 2018. It's an excellent partnership. Our Mars 2020 landing, and then other missions that we're in formulation right now. Missions like WFIRST and others that we want to continue on this excellent partnership.
You recently announced that you're retiring from NASA. This must definitely be retiring on a high note.
Oh, this is an extreme high note. I'm very honored and privileged to be over here to share this moment with our ESA partners. But yes, for me, this is extremely exciting for me.
All right. Well, congratulations and good luck for the future. And thanks for joining us in this program.
Thank you.
All right, Steve, one of the things you mentioned very early on was the fact that we didn't have a lot of information about comets. And that's one of your specialties. You've been involved in 5 flybys of comets for NASA. That was pretty much what we used to do, is just fly by, take pictures, take a look. What are we looking at now after a mission like Rosetta?
Yeah, the flybys, of course, have set the stage for a mission like Rosetta. You get these snapshots, and you know what you're going to look for. And so the amount of time spent at the comet and seeing the comet evolve right before our eyes has been sort of the key linchpin. We've always said, as long as I've been studying comets, that the more we learn about comets, the less we know about comets. And I think with Rosetta, we're sort of turning the corner on that question, and we're really starting to now grapple with and close some of these really big questions. We've heard about these understanding the early formation of the solar system and how you get from gas and dust to small pieces, meter-sized pieces, which maybe are these dinosaur eggs, and how they come together to form planetesimals, which are the two lobes of this comet. It was very fortunate, I think, to see a two-lobed, a bilobed comet, which is probably the rough majority of comets have two lobes. It was great to have this opportunity to see so close and for so long this kind of configuration.
Were there any huge surprises with this particular mission and this particular comet?
So, yeah, we might talk about the water, I think, because there had been, I think, a lot of scientific momentum towards explaining the presence of water on Earth as being delivered by comets. We know that comets have a lot of water in their chemistry. And one of the instruments from Rosetta was able to show that this deuterium to hydrogen ratio, sort of the difference between heavy water and ordinary water, it's like a fingerprint for water. The water on the Churyumov-Gerasimenko, the Rosetta target, is different from the water on Earth.
Different, how so?
Well, this ratio of deuterium to hydrogen in Earth's oceans is not very close to that we see in the comet. So comets like Churyumov-Gerasimenko could not have delivered all of the Earth's water. Now we're looking at other ideas. Asteroids, although they appear dry and dusty, they actually have water molecules sort of entrained within their minerals. And it looks like, from measurements that have been done so far, that water might be a better match for the water that we have here in our oceans.
All right. Well, we are told that we have another guest over at ESA, but before we go to that, one of the comments made during the commentary I found very interesting. The person had said, by understanding comets, we can protect ourselves. And what did he mean by that?
Yeah, comets and asteroids have been hitting the Earth for billions of years. And in the context of we should know our enemy, comets and understanding them helps us both understand the past. These objects have affected the Earth's biosphere. They have affected the evolution of life on the planet. And the more we understand about them, the better we understand our own planet. We also can better understand our future. The more we understand these objects, the better we are prepared to react to something that might be a crisis in the future.
And that's something you do on an everyday basis with the Near-Earth Object Studies.
Yeah, at our Center for NEO Studies here at JPL, one of our main jobs is to keep track of all the asteroids and comets and make sure that none of them are going to be threatening the Earth. And if they are, we sort of notify. We have a website where we keep all these possibilities up, and that allows observers to get more data and better understand the problem.
All right. I'm being told that our guest is seated and ready to go. So before we go, we are going to speak with the U.S. Rosetta Project Manager, Art Chmielewski. Art, are you there? Oh, yes, he is. And
Checking
with a
in.
Rosetta in tow? A Comet in tow. Art, excuse me. Let's take a moment. I mean, for you, Art, what do you think are the big takeaways from this particular mission?
Well, to me, it's a great triumph of humanity, really, of engineering, science, moving forward with knowledge, and also international cooperation. 12 countries working together for common cause, helping each other, using the best of each country to make sure that this mission happens. Great triumph, any way you look at it.
Art, one of the things I'm wondering about, you've been with this mission for a while. We saw sort of a nail-biting situation trying to land on a comet. What are some of the other, and maybe what are the most memorable nail-biting moments for you as part of this mission?
Well, this was a long flight. It was 12 years. But to me, with my engineering background, the most exciting actually times were before we even got to the comet. Because we had to fly past the orbit of Jupiter. That's very far away. That's solar panels see kind of sun there as a little dot. So we didn't have a lot of power. We had only enough power to keep the spacecraft warm and maybe the computer running. So ESA had to put the spacecraft to sleep. So the spacecraft was so-called hibernating for 2.5 years. And that was the first time that anybody put spacecraft to sleep, and especially for such a long time. And I was afraid for these 2.5 years that the spacecraft was sleeping, I was thinking, one particle hits it. And in these speeds, we're talking 50, 60, 70,000 kilometers an hour. Tiny collision is basically death. A little heater delaminates and stops heating the computer. I mean, you can postulate hundreds and hundreds of scenarios where the spacecraft would not emerge from sleep. So when the time came to wake up the spacecraft 2.5 years later, I was sitting in front of the monitor waiting for the radio signal to come, and it was supposed to come at 10 a.m., and I was staring at the screen and trying to make the signal reemerge, and it did, but 16 minutes later. But these 16 minutes were like 16 years for me. Maybe that's why I look so old. You don't realize, but I'm 23 years old, actually.
So are we done? Are you done with comets after Rosetta?
Well, first of all, we analyzed only about 5% of the data that came from Rosetta. So now it's the busy time. Now, not only are we going to be looking at the data of each instrument, but now all the principal investigators, all the scientists, they will be coming together in groups and comparing the data. Okay, the dust instrument, what does it say? The microwave instrument, how does it compare to the ultraviolet instrument? So there's years of hard work ahead just from the data of this comet. And then we're shifting over our sights to the next mission. So we're looking at other places where life may exist. We know that possibly comets brought these ingredients for life to Earth, and now maybe life is somewhere there. We're looking at Titan. We're looking at comet sample return. We're looking at Enceladus, places that potentially may harbor life. So the excitement continues.
Absolutely. Well, Art, thank you so much, and congratulations to a hugely successful mission, and congratulations, of course, to ESA.
Goodbye, 67P, Cheremov Gerasimenko.
Thanks, Art. Well, that wraps up NASA's coverage of the Rosetta mission. Our thanks to Steve Chesley for being our comets expert. And if you would like more information about Rosetta, visit the site at rosetta.esa.int. And for more on NASA's role in the mission, go to rosetta.jpl.nasa.gov. Thanks for watching, and congratulations to ESA for a hugely, hugely successful mission. Well done.